Hello, this is the second part of the video, so let's continue. So if we do it correctly, we will get the equation, the Boolean equation as below. F of A, B, C and D is equal to not A, not C, not D plus A and not B plus C and not D. So this is the Boolean equation. So observing the equation, we notice that we can actually simplify it further. So how do we do that? So we can do that by using De Morgan's theorem. So De Morgan's theorem basically allows us to actually break or merge the bar on top of the terms. So as you can see, A, C and D, all of them have a bar above them. So we can actually merge it together as one big bar. So by doing that, the inside the bar we will have A plus C plus D. So that is De Morgan's theorem. So by utilizing De Morgan's theorem, we will get the equation as below. So it is a slight different from the equation, but it will yield the same output. So what do we do with this Boolean equation? So from this Boolean equation, we can construct the logic circuit. So this is the logic circuit. As you can see, there are four inputs, A, B, C and D. And this is the output, which is we use a bulb as the output. So when the bulb is not light up, it is output 0. And when it lights up, the output is 1. So let's analyze the logic circuit. So as you can see, we have 1, 2, 3, 4, 5 and 6 gates that we use for this logic circuit. So the reason why we actually simplify the equation, the previous equation, is to minimize the number of logic gates used for the logic circuit. So compared to the first equation, we will actually use 8 gates. And for this circuit, we only use 6, which is much less than the first one. So this is the NOT gate, this is the AND gate, and this is the NOR, or you can also say it as NOT OR. So this is the one that we use the De Morgan's theorem. So A plus C plus D is actually A or C or D, and with the bar on top is NOT. So NOT OR is actually NOR. And we will go to the last gate, which is the OR gate. We will take the input from the NOR and from the two ends, and the output of the OR gate will go to the output overall. So this is the logic circuit. Next, we will try to use universal gate to construct the same circuit with the same output and inputs and outputs. So what is actually universal gate? Universal gate is when we can transform the circuit that we got previously from using many types of logic gates to only using one type of gate, which is the NAND gate, or also known as NOT AND gate. And this can be done by using De Morgan's theorem to transform the equation into another equation that utilize the universal gate. So let's see how it's done. So by using the logic that A is equal to not A, so this can be proven as, let's say the input of A is 0. So the output of not A is actually not A is 1, and not A will be 0. So with double not, it will revert back to the original. So by using that logic, so this is the original equation that we have. We will put a double bar above it, and from the double bar we can use De Morgan's theorem. So by using De Morgan's theorem on the equation, we will split the lower bar first. So by splitting the lower bar, we will get that the plus will be times. And this is the resultant. So as you can see, the not A, not C, not D will have a bar above it times A and not B with a bar above it, and C and not D with a bar above it, and one big bar above all them all. So if we observe carefully, every term is now in NaN form. Why? Because not A times C, not C times D, and a bar above it. So A and C, not A and not C and not D with a bar above it. So it is NaN. Same goes for the second and the third term. So every term now is in NaN form. And all of it, so the first term times the second term times the third term with a bar above it is also NaN form. So this is how we use De Morgan's theorem to transform the original equation into an equation that satisfy the universal gate. Yes. So next, how do we construct the circuit? So first of all, we need to know how to construct an OR gate using NAND gate. So this is how you construct an OR gate using NAND gate. So the same inputs will be given to one NAND gate, and the output will be it's like it functions just like an OR gate. So let's say that the input is 0. So 0 and 0 will result in 0. But this is NAND gate, so 0 inverted will be 1. So when the input is 0, the output will be 1. And let's look at what happens if the input is 1. When the input is 1, 1 and 1 will result in 1. But this is the NAND gate, so the 1 is inverted into 0. So when the input is 1, the output will be 0. So this is the OR gate equivalent using NAND gate. So with that out of the question, we will be able to construct the circuit, equivalent circuit using only NAND gate. And this is the circuit. So by using only NAND gates, we are using 1, 2, 3, 4, 5, 6, 7 and 8 NAND gates. Only 8 NAND gates are needed to construct an equivalent circuit. So as you can see, there are a lot of this is actually not. It's not or it is not. Sorry, my bad. There are a lot of NOT gates that are used in the equation, such as NOT A, NOT C, NOT D, and NOT B. So as you can see, we use around 1, 2, 3, and 4 for each inputs. We have the NOT gates for them, which is constructed using only a NAND gate. So this is the equivalent circuit using only NAND gate, which is a universal gate. So last but not least, we should take a look at the simulation to see the functionality of the circuit that we constructed. So this is the circuit that we constructed. So you can take a look at the truth table, and you will get the same output as indicated in the truth table. So when the input is 0, 0, 0, 0, the output is 1. When the input 0, 0, 0, 1, the output will be 0. Next, 1, then 0, then 1, then 0, 1, 0, 1. This is the ninth output. So for the 10th, it's still 1, 1, 1, and then 0, 0, 1, and 0. So that is all the combination of the inputs that we have and all the resultant outputs that we get. So I think that's all from me. I hope that my explanation is clear and helpful in guiding you to actually solve the question of the midterm project. So with that, I conclude my video and presentation. Thank you and have a nice day.